The goal of this video is to focus on thermochemical equations, understanding what information you can get from them, and then also looking at the sign on Q again. So to start with, one concept you continually have to work on throughout this unit is that relationship to heat in versus heat out and the sign on Q, or heat, right? So when we have a scenario where we have heat leaving our substance, whether that means it's getting colder or it's reducing in its potential energy, that's always exothermic. So energy out is exothermic, and exothermic is shown by a negative sign in front of the value on Q. If instead you're gaining energy, so you're getting hotter in temperature or you're increasing the potential energy of the system, either way you're going to end up having positive Q then. The heat will be positive for whatever you're working with. So make sure you have that negative sign or the positive sign to indicate the direction, whether it's out or in. These graphs show you specifically for potential energy as we start to think about the potential of a system, whether it's the potential due to a chemical bond or an intermolecular force. So whether it's a bond that will break in a chemical change or a physical change. If our potential is higher to begin with than in the end, that would be considered an exothermic change, versus if it gets higher at the end, that would be endothermic. So these are energy diagrams, and you should be able to identify which one's endo and which one's exo. So to quantify when we are dealing with heat changes that don't necessarily involve a temperature change, we use a label called enthalpy. And enthalpy is sometimes referred to as molar heat because enthalpy is specifically the heat available per mole of something. This calculation for heat specifically has to do with the internal energy, so really the potential energy of whatever substances we're looking at. One huge thing about enthalpy then is delta H is measured in kilojoules instead of joules, and it's per mole. So Q is just joules, right? How much energy is transferred, lost, or gained, where enthalpy is joules, or specifically kilojoules per mole. So how much energy is there per amount of substance. Another thing then is we will never be calculating enthalpy straight up, like it will never be H equals, like how we have Q equals. We're always going to have a change in enthalpy, and that's because it's really hard for us to actually calculate the internal energy of a system. It's much easier for us to see how much energy was transferred during a change and quantify that. So one type of change we may experience is a chemical reaction, right? From the start of a reaction to the end, bonds are broken and formed. And during the process of bonds being broken and formed, we have a change in potential because the potential energy is all about the energy stored in the bonds. And as we form new bonds, new potential energy numbers or amounts are generated. So when we talk about the energy for a reaction, we calculate the enthalpy of the reaction. What was the enthalpy change going from reactant to product? So the delta H of the reaction, or the enthalpy of the reaction, or the molar heat of the reaction, is just the enthalpy of the products minus the enthalpy of the reactants. We can't calculate the H of the product or the H of the reactants, but we can calculate the delta H of a reaction as the reaction proceeds. So these delta H of reactions are standard values you can find in books. They're measured at something called standard conditions, which is 1 atm and 25 degrees Celsius. The other thing about any delta H is they're state specific. Since we're talking about the potential energy of the system, if you change the state of matter of one of your reactants or products, you'll change the total energy change. So when you write reaction and that includes the thermochemical information, essentially you're including the delta H of the reaction as part of the chemical reaction. So in the past, we simply put a triangle either in the products if it was exothermic or the reactants if it was endothermic. Back when we were writing equations, if there was a heat change, we just noted that with a triangle. Now in this unit, you have specific values for the energy change. If it's exothermic, not only are you placing heat as a product, but you're specifying how much heat is related to that energy change. So a thermochemical equation is simply an equation that indicates what is reacting, and it's balanced with the coefficients, but it's also telling you how much energy was transferred. So in the first example here with methane, during the course of that reaction, 890 kilojoules of energy is given out. And we can tell that it's given out because it's a product. We can also tell it's given out because when we write it independent of the reaction, as delta H of the reaction, there's a negative sign on it. And the negative sign on it indicates direction. It's out. For the other reaction, for the decomposition of water, to get water to decompose, you have to put 241.8 kilojoules in. So that's endothermic. That's a positive energy. Essentially, we need to put more energy into the relationship than what was there for the water. So to write a thermochemical equation, you just have to write a balanced chemical equation that includes states of matter and the amount of energy due to the reaction, either as a product if it's exothermic or as a reactant if it's endothermic. What you can do with a heat of reaction is stoichiometry. So by stoichiometry, I mean that in the past, when you looked at a chemical reaction, there was a relationship between the two different substances in your reaction. So for example, for the magnesium reaction with oxygen example, you need a 2-to-1 ratio of magnesium to oxygen to make the relationship happen. Now we have thermochemical information, and essentially that reaction produces 1204 kilojoules of energy per mole of the reaction. What that means is when you have a 2-to-1 relationship of magnesium oxide, for every 2-to-1 that exists, 2 moles to 1 moles, you make 1,204 kilojoules of energy. If that reduces in half, so now I have 1 mole of magnesium and half a mole of oxygen, I get half the amount of energy out. So it's a consistent relationship that for every 2 magnesium, it's 1,204, and for every 1 oxygen, it's 1,204. And if you adjust them, you adjust the amount of energy released. So given a real scenario, like the one on the slide, how much heat is needed if I react 22.1 grams of sodium bicarbonate? Sodium bicarbonate has a 2 to 129 kilojoule relationship. If I have a gram amount, I've got to get it to mole to be able to relate them. So what this looks like when you set up the stoichiometry is right here on the screen. You take that 22.1 grams of sodium bicarbonate given, get it to moles of sodium bicarbonate, and then you used a mole to energy relationship of the delta H of the reaction to solve just for the reaction heat amount given a specific amount of sodium bicarbonate. So essentially it's stoichiometry, gram to mole, but instead of going gram to mole, mole to mole, you know, gram to mole, mole to energy, given the heat of the reaction is a specific amount of energy per mole of the reaction. So another example right here, what is the enthalpy change if I have 18.15 grams of nitrogen reacting with excess oxygen? Step 1, you got to figure out what's going on with delta H, if it's endothermic or exothermic in terms of what your final answer should be. Then you're going to get the quantities into mole and then use a mole to energy ratio to solve for the amount of energy of that specific amount of nitrogen. So you take the grams of nitrogen, using the molar mass, get it to moles of nitrogen, and then use the mole to energy ratio using the coefficient of the nitrogen to the amount of energy of the reaction. Another way that we quantify enthalpy is if we are dissolving something. So if we have something that's dissolving, we have the ionic attraction between the salt breaking and new ion dipole attractions being formed. So we have a change in potential energy as we change the attraction. So there's heat energy required to release. So there's heat energy associated with that change of the attraction between the ionic compound versus the attraction between the ion dipole. So sometimes they get hot, sometimes they get cold, depending on that difference. But you can have also a delta H of solution where the process here is dissolving instead of a chemical reaction. The other delta H we can have is a delta H of a phase change. When we change phase, we are not putting any temperature. When we change phase, we're not changing the temperature. We're simply changing the potential energy. So we can do a delta H of that change. On the screen here are just the words associated with those changes, just so you're aware of how we quantify that. Now, because a phase change does not include a chemical reaction, in order to relate your amount of energy to the specific amount of moles present, we use this equation. So in order to calculate the Q for a phase change, we take the delta H and multiply it simply by the moles instead of the mole ratio scenario because we don't have a chemical reaction. So that's it kind of for your overview of enthalpy. Go ahead and do the form and have a nice night.